Bismillahirrahmanirrahim. Today we will discuss the asymmetric synthesis by substitution reactions. We have already discussed that what is asymmetric synthesis. Now we will consider the SN1 or SN2 reaction, the substitution reaction involved in asymmetric synthesis, and the different factors like leaving group, their stereochemistry, and nucleophilicity of nucleophile affecting the SN1 and SN2 reaction during asymmetric synthesis. Okay, so the asymmetric synthesis by substitution reaction, the reaction is R1 R2 is attached to the R1 R2 R3 attached to the carbon, and the leaving group is also attached with the carbon. Means this is a substrate. LVG is a leaving group, plus we have Nu is a nucleophile carrying a negative charge, and they're giving us a product plus leaving group. Okay, so we have a question here. We have two reaction SN1 and SN2. Which one is suitable for asymmetric synthesis and why? Okay, which one is more suitable and why? So before going to answer this question, we have to compare these two reaction mechanism or reaction features so that we will be able to answer this question. Okay, so first property is the order of reaction, that is kinetics. SN1 is the first order reaction and SN2 is a second order reaction. Okay, what is first order reaction mean? It is the first order reaction means that the substrate involved in it, only the reaction depend upon the concentration of the substrate, while in the second SN2 reaction, this is second order reaction, means it is first order with respect to the substrate and first order with respect to the nucleophile. So overall it is a second order reaction. 1 plus 1 is equal to 2, so it is a second order reaction. In SN2, the nucleophile plus substrate both are responsible for the formation of the product. Okay, while in the case of SN1, only substrate is responsible, or the rate of reaction we are talking about specifically rate of the reaction are dependent only on the substrate, while in the case of second order reaction, that is SN2, the rate is dependent on the nucleophile as well as the substrate. Okay, the next is mechanism. SN1 is a stepwise reaction, while the SN2 is concerted reaction. What is concerted reaction? Means the bond making and bond breaking takes place. Bond making and bond breaking take place simultaneously. In simple words, we can say that in a single step, the bond breaking and bond making is taking place. Okay. While in the case of SN1 mechanism, we have a stepwise reaction. First step involved is the formation of carbocation, while the second step involves the attack of the nucleophile. So first step is a slow and second is fast, and the slow step is a rate determining step. Anyhow, we have to focus on and the mechanism. This is a two-step mechanism. Now we talk about the stereochemistry. Stereo means with respect to space. Okay, stereo means with respect to space. SN1 reaction are not stereo specific. Racemization occur, mean 50% of inversion and 50% of retention of configuration takes place. While in the case of SN2 reaction, we have a stereospecific reaction. What is a stereospecific reaction? The stereospecific reaction are those reactions in which we get only one product, mean there is a no formation of mixture. Stereospecific mean we have a specific product for a specific reactant. There is a no formation of mixture, as in the case of SN1, that is racemic mixture formation takes place during the SN1 reaction. Okay, so SN2 gave us only one product, while in the case of SN2 gave us one product, while SN1 gives the mixture of product. And if we talk about the substrate, with respect to the substrate, SN1 prefer the secondary and the tertiary substrate, third degree and second degree. The third degree means we have a substrate for SN1, that is tertiary alkyl halide, and the secondary alkyl halide, while SN2 prefer primary and secondary. The SN1 prefer the tertiary over secondary. Why? Because there is first step. I already mentioned that in SN1 reaction we have the formation of carbocation in the first step. During the formation of carbocation, stability matters a lot. Third carbocation, third degree carbocation or tertiary carbocation is more stable as compared to secondary and primary. That's why SN1 reaction prefer secondary, tertiary carbocation over secondary, and secondary carbocation over primary. If we have a reaction and there is a substrate of secondary or tertiary origin, then we can say that SN1 reaction will be preferred. If there is a primary or secondary, we can say that SN2 reaction will be preferred. Nucleophile and leaving group. If we talk about the nucleophile, nucleo mean nucleus and phile mean loving. Nucleophile mean nucleus loving. In SN1 reaction, the good nucleophile works, and while in SN2 reaction, strong nucleophile is best. Same in the case of leaving group, good leaving group is preferred in SN1, and then SN2 good leaving group is preferred. We will discuss both these two, leaving group and the nucleophile, one by one after this slide. For being stereospecific, SN2 reaction on the secondary substrate are more reliable in asymmetric synthesis. G. We concluded that, and we highlighted it with a green. Green mean it is a favorable. If we saw the heading of stereochemistry, it is also green, and SN1 heading is red, and red is alarming, not suitable. While in the case of SN2, here we have again green color, and at the end of this we concluded that the being a stereospecific, SN2 reaction on the second substrate or the secondary substrate are more reliable in asymmetric synthesis. Here we decided that in the substitution reaction of SN1 and SN2, we preferred SN2 reaction for the asymmetric, synthesis. Okay, we preferred the SN2 reaction for the asymmetric synthesis. Why we preferred the SN2? Because of its stereospecific nature, mean it gives only one type of product. There is a no formation of mixture, so we will get our our desired product, and there is a no formation of any product in this reaction. Okay, asymmetric synthesis, SN2 reaction, the strong nucleophile needed. As I already mentioned, nucleophile is nucleus loving. Nucleo mean nucleus and phile mean loving. It means it is electron loving species, is an electron rich species that has a negative charge or at least a lone pair of electron. Okay, it has a large number of electron, but it does not has any home to occupy them or to adjust them. So it is willing for a nucleus so that it can easily encounter the electron. Okay, and stabilize itself. There are generally three factors that determine the trend in the nucleophilicity of a reactant. Here we have the three different factors that which are involved in deciding the nucleophilicity of a nucleophile. That is, which one is going to be a strong nucleophile, which one is going to be a weak or a moderate nucleophile. On the base of these 3 points, we will be able, after studying these 3 points, we will be able to categorize the different nucleophile, whether it is a strong nucleophile, mean good nucleophile, moderate, or a weak nucleophile. The first factor is the size. The more linear or a smaller nucleophile is more nucleophilic, the more nucleophilic it will be. It avoids steric hindrance if it is a smaller or linear. Means if a ligand is a small, sorry, if an atom is small or a group of atom is a small, that is we can say that if a nucleophile size is small or it is a linear, so it can easily attack the substrate without interacting the steric hindrance of the bulky group of the substrate. Okay, if its size is large and it is not a linear, it has its own steric hindrance, and its own steric hindrance interacts with the steric hindrance of the bulky group on the substrate, and the attack of the nucleophile is compromised. Due to this, the ability or the attacking efficiency of the nucleophile to attack on the substrate is also compromised, and we can say that this is not a good nucleophile. The second point is electronegativity. Its definition is the ability of an atom to attract the shared pair of electron towards itself. No, we read the statement, the more electronegative an atom is, the less nucleophilic it will be. And it means there is an inverse relation. Nucleophilicity decrease across the periodic table. Okay, now we will understand this, how electronegativity affect the nucleophilic character. If a compound is more electronegative, if a atom, you can say that if a atom is a more electronegative, it's mean it is more willing for an electron as compared to nucleus. Because a nucleophile mean it is a nucleus willing, yeah, you can say that it is nucleus loving. If a atom is more electronegative, it means it is more willing for an atom, more willing for an electron as compared to nucleus. Okay, so it will attract the electron toward itself. It means it is not a good nucleophile, but you can say that it is a good electronegative atom. The more electronegative atom is, the less nucleophilic it will be. So by looking the trend across the period, the carbon is less electronegative. It means it is more efficient nucleophile as compared to nitrogen, and nitrogen is more efficient than oxygen and fluorine. Why? Fluorine is the highest electronegative atom in the periodic table. Okay, in the periodic table, then oxygen and then nitrogen. Because of the high electronegativity of fluorine is the least nucleophilic in a character. Okay, if we talk about the third factor, that is the polarizability. Polarizability means creating the poles to gain stability. More polarizable an atom is, the more nucleophilic it will be. The best and the most efficient example is the iodine. Iodine is good leaving group as well as a good nucleophile because of its polarity. Why it has high polarity? Because of its large size, it can easily polarized. Mean, if a substance easily polarized, it has a large size, so it can easily stabilize itself. That is I negative. So iodine is the best nucleophile as well as the best living group. So here we can also relate polarizability with electronegativity, as the top to bottom the electronegativity decrease. So we can say that electronegativity decrease, the size is increased, and polarizability a factor is increased, so nucleophilic character is increased. Okay, so here we have characterizes some nucleophile as a strong, weak, and moderate. The best or very good nucleophile are, starting from the bottom, very weak nucleophile are CO2H. It's mean they are carboxylic acid, and weak nucleophile are water and alcohol, and the fair are ammonia, chloridine, fluoridine, carboxyliatine, and the good nucleophile are bromidine, hydroxidine, ethoxyine, cyanidine, and three negative is azidine. And very good nucleophile are HS negative, I negative, and RS negative. They are thio compounds, that is, which contains S atom are called thio compounds. Iodine are the best because of the large size and high polarizability. Why? The carboxylic acid, that is RCO2H, is a very weak nucleophile because it has two oxygen atom that are which are both highly electronegative atom. Here we are not differentiating oxygen. I just mentioned it. Both are both oxygen atom. It is simply oxygen atom. Okay, oxygen atom are highly electronegative, and we have discussed that the with electronegative atoms, the nucleophilic character has inverse relation. Higher the electronegativity, lower the nucleophilic character. Okay, so the best nucleophile should also be a weak basis. This is very important thing. The best nucleophiles are should also be a weak basis to limit the competition between the substitution and the elimination. So here we have drive the conclusion, or we concluded that the substitution is preferred over elimination. Mean, we eliminated the E1, E2, E1CB and other elimination reaction on the behalf of the nucleophilic character, so that we concluded here that in during the asymmetric synthesis we have SN1 and SN2. In both of these we prefer the SN2. Why? Because of stereospecific character, and by the category of nucleophile we will be able to draw the conclusion that the substitution is preferred over elimination during the during the presence of very good nucleophile, because very good nucleophile will act as a weak base, and if the base is strong it will go toward the elimination reaction. Here we have the synthetic targets SH, that is source sodium, SH, RSNA, that is the thiols such as cysteine, thioglycosides, alkyl iodides, alkyl bromides, and cyanohydrin, and the primary amines. and the azide, that is chiral amines, are amino acids or amino acids. These are the sources or the synthetic targets of the nucleophile, depending upon their strength. Asymmetric synthesis. SN2 reaction. Here we will discuss the role of a leaving group. Before going to the discussion toward the leaving group, we have to understand what is the leaving group, how it interacts with how it bonds with the substrate. In simple, if a leaving group has a strong bond with the substrate, it means it will be difficult for us to break that particular bond. Number one. And the second thing is its stability. If a leaving group, after leaving the substrate, it is not stable or stable, both things we consider for deciding its activity as a living group. First, we will consider as its stability, whether it is stable after the leaving the substrate or not, and the second is its interaction or its bonding with the substrate. Both these two factors helps us to understand the chemistry of living group and its category, whether this is a moderate, strong, or good a living group. Okay, the living group, we have a definition, is an atom or group of atom that displays as a stable. Yes, displays as a stable species, taking with it the bonding electrons, mean it moves or it leaves the substrate along with the electron. Okay, so the leaving group may be an anion or a neutral molecule, that is water. The better the leaving group, the more likely it to depart. The more stable a leaving group, it is more favor the living. Definitely, if a leaving group is stable, it means it will leave the substrate immediately. And in other words, we can say that it has a weak bond with the substrate. We will discuss this, the bonding with the between substrate and the living group, after discussing this example. The best living group is the p para toluene sulfonic acid. Why? Before going to this question, we will discuss the para toluene sulfonic acid as a acid, whether it is a strong or a weak. Some of the strongest organic acids are the sulfonic acids. Okay, here we have the sulfonic acid. Its conjugate base is p toluene sulfonate. Okay, plus it is giving us H positive ion. Consider it, and we will move toward the next slide. Here we have the classification of the leaving groups. The excellent leaving group is TSO negative, that is p toluene sulfonate. Okay, why it is better leaving group? Because if we focus on the structure of this compound, we see that this is highly stable after leaving the substrate. Why? Because it is resonantly stabilized. Why there is a resonance? Because of the presence of benzene ring, its electron is delocalized. Mean this is a highly stable. Because it is highly stable, as we already mentioned in the definition, that is a living group is an atom that is displayed as a stable species. So we concluded that the p toluene sulfonic acid
if it is attached to a substrate, it will act as a strong living group. Because why it will act as a strong living group? Because it has strong or stable, strong, not mentioning here strong, it has a stable conjugate base. Or after departing the substrate, after leaving the substrate, it will convert it into that species which has highly stable. Here we are saying we have discussing the different groups according to their ability as a living group. For example, we have second, on the second number we have iodine and water. We already discussed the iodine, that iodine, due to the polarization, it has a high ability, it has a good it has the ability to act as a nucleophile, good nucleophile, as well as a good living group. Water. While discussing the water, we have seen that the water is very stable species. Because water is present in H2O form, and in daily routine we have a lot of reaction in which water act as a neutral species. Although water has a reactivity, but overall water is highly stable. Okay, so in general we can say that water is highly stable, as we can experience it during whole day exercise. Okay, good living groups, that is bromide. Why? Up now you can see that the very good category is iodine, and the good category is bromine, and the fair category is chlorine. Because the bromine is at the top of the iodine, and it has less size, so it is a good category of it is it lies in the good category of the living group because of its smaller size as compared to iodine. Similarly, for a chlorine lies on the top of the bromine, and the chlorine size is smaller than the bromine, so it lies in the category of fair. Okay, and the fluorine is the very poor because of its small size. And here I will mention that the fluorine is the very poor living group because of its very small size, and because of its high electronegativity. It will bind with the substrate with more power, because it has with more with a strong bond, because it has high electronegativity difference, and its conjugate base, that is F negative, is not stable. Okay, so and the very poor groups are the HO negative and 2 negative or O negative. Here reason is the same, because oxygen and the nitrogen both are electronegative atoms. Okay, so generally the order of living group ability is as follow: TSO negative is excellent, then iodine. Now you can consider the group 7. The top to bottom size is decrease. You can say that the electronegativity, in other words, electronegativity top to bottom electronegativity decrease, and top to bottom size is increase. Both these two factors involved in deciding the nucleophilic character, that is iodine is a negative, TSO negative is excellent, while after that the iodine, then bromidine, then chloriodine, and that the fluoriodine is the poor one. So up to here I completed my part of I completed the my part of presentation, my presentation part up to here. If you have any question, you can ask or you can comment on comment section. I conclude this by summarizing all my presentation, that at the start of asymmetric reaction we have to synthesize a product by a substitution reaction or a elimination reaction. For leaving elimination reaction on the side, first of all we interact with the substitution reaction. In substitution reaction we have in substitution reaction we have two types of reaction, that is SN1 reaction and SN2 reaction. And SN1 reaction and SN2 reaction, in these two reaction we decided the SN2 reaction is a better for asymmetric synthesis. Why it is better for asymmetric synthesis? Due to its stereospecific nature. What is stereospecific nature? Mean it gives us is only one product. There is a no formation of mixture. So while in the case of SN1 we have a mixture, that is racemic mixture of a product, so we will prefer the SN2 over SN1. And by deciding the nature of nucleophile, we come to know that if we have a good nucleophile that will act as a weak base, so the possibility of elimination reaction is eliminated. And we in during my presentation we concluded that how we categorize the different compounds, atoms or group of atoms, as a weak, moderate and a strong leaving group, and weak, moderate and a strong nucleophile. That's all. Thank you so much. Allah Hafiz.